So I believe where we ended was looking at our acid-base steps and kind of mechanistic extras on discussing on what makes a good or bad mechanism. One of them we addressed with that top one. Actually, we did both of these, right? Yes. That in that top one, it doesn't make sense to show that as an intermediate mechanistic step because we're now generating a strong acid in a basic environment. So that is conflicting information. That makes this mechanism bad. Right. Same kind of deal with the bottom one. I'm in a strong acidic environment, and I say, well, that's not that big of a deal because I have a strong acid there, but what else am I producing? I also have that strong base. So when you go through and run a mechanism, be cognizant of your acid or base conditions because those acid-base conditions can shut down individual reactions and can get you a pretty significant loss in points. Okay? As you'll find as we move through chemistry into second semester, if you happen to go there, there are cases where the base conditions get you really short mechanisms. You're like, oh, I always want to run base conditions, but then you almost always test it on acid conditions, and it like triples the length of the mechanism. Right? So don't shorten a mechanism. Do what is necessary to run the reaction. Okay? Along those lines, in both of these cases, what we want to be doing is identifying the most reactive thing present and neutralizing it. What is all too common, the top one's the easiest one to look at, so let's look at that one. What is all too common is students will go through and look beginning to end and say, oh, well then that oxygen and that carbon have to be connected, so I'm just going to do it. Okay? I don't care about anything else. I just know that that has to happen, so I'm going to do it. The problem is you didn't address the chemistry in the reaction. The reaction says you're running under basic conditions. That is the most reactive species in the purple. I don't care what I want to do. What I have to do is neutralize the reactive thing. Okay? Let's pick a bad analogy because it's always fun. Mario wanted to hook up with the princess, right? Make it to the princess. Did he just run to the princess, or did he have to jump through and defeat a bunch of enemies along the way? He had to defeat a bunch of enemies along the way, right? Why don't you just skip the enemies and go straight to the princess? The enemies were in the way. Okay? You have to deal with the things in the way before you can make it to the target. Most of you want to go into some pre-health profession. What's your enemy in the way? Okay? You have to make it through this class before you can get there. Okay? So deal with the class first before making it to that end goal. Okay? That's always fun. I love being the bad guy. Okay? Kind of makes sense? Okay. So one of the things that we talked about, and I believe it was you, Cass, that asked about it, trying to run an intramolecular reaction. So if we take a look at the reaction shown here, okay, we've got a mechanistic step set up. The nitrogen being a source of electrons will do a backside attack and kick out the oxygen as a leaving group. This one's a bit weird because that oxygen leaving group is still attached to the structure in the product. Okay? Leaving groups don't have to leave the structure, they have to leave the atom to which they were attached. Okay? So that's kind of a bizarre looking system, but that is an SN2 reaction. The result is we would end up with that intermediate, with the positively charged nitrogen and the negatively charged oxygen. Okay? To be extra misleading, we could look at the product, and when we look at the product, what needs to happen? What things need to change? I need to get rid of a hydrogen to the nitrogen and
gain a hydrogen to the oxygen.
Gain a hydrogen to the oxygen. Okay? So, well, why not just go through and say, well, let's draw on those hydrogens and have this oxygen come over and take that and do that. Why not do that? Okay, the issue with that is we have 1, 2, 3, 4, 5 atoms in that ring. Okay? Those 5 atoms in that transition state, the likelihood that they all rotate so that those two, 1 and 5, are close enough to each other to actually form a bond is so rare that it doesn't make sense to show that as a mechanistic step. So what does that mean our mechanism has to be? I will take NH3 as a solvent. Those electrons will react with that hydrogen to give me a product. That product would now be 2 with the electrons. There's my O minus. I would then generate NH4. Plus, now what can happen? The electrons from the oxygen can share with that hydrogen, react, go back to the nitrogen, to end up, to end up with the final product. But isn't it shorter to show that as one step? Yes, that doesn't mean you're allowed to do it. Okay? It doesn't mean it makes physical sense to do it as one step. It makes more sense to have the solvent-mediated acid or proton transfer. Okay? So there are limited cases for intramolecular reactions. Typically, they don't happen. Okay? So of course, what's the very next thing I show? It happens. Okay? I can get intramolecular reactions to happen. Okay? There are very limited cases that allow it to occur, but those conditions kind of have to be set, and ultimately it comes down to saying, well, I know this is the product, it has to happen, so I'm going to do it that way. Okay? How does this reaction work? The electrons from our hydroxide react with that hydrogen. So we do an acid-base step to make our negative oxygen with all its electrons. And then our bromine. And get ready for the fun question on this one that you guys get to answer. The electrons come in, attack, and kick out the leaving group. Okay? Notice this is a backside attack. The negative oxygen is attacking from the backside of the leaving group bond. Okay, everybody see that? Wedged oxygen, dashed bromine. Okay. What was the first mechanistic step? What kind of reaction was that? So reaction 1. All it was a transfer of a hydrogen, so we did an acid-base step. What happened in the second step? It's an SN2. Okay. But what's the nucleophile? I only see one species that I'm starting with. I don't have two. Where's my nucleophile? It's the oxygen that's attached to the structure. Okay. So we can get these kind of weird patterns in that you don't like doing them, okay, because they don't fit the standard protocol that you've already seen. But that standard protocol is because we're trying to make it easier to see. Okay? And it's easier for you to see two things interacting with each other than having one thing interact with itself. It is still possible to happen. Okay? Conditions have to be perfect, but they can happen. Okay? We started with what kind of a functional group? We have an alcohol and a halogen on one compound. This is typically referred to as a bromohydrin. Bromo because it has bromine, hydrin because we effectively have water attached to this structure in the OH. Okay? So that is a bromohydrin. The product one you should actually know, sort of. That is an epoxide. Okay? Those become much more relevant in the next unit, so we'll be super excited with those. Okay? We will see those pop up all over the place. Those also become extra fun when it comes to spectroscopy. Okay? One more thing before, I don't know why I didn't show the other one first, but oh well. If we take a look at these two reactions, what happened? What kind of reaction happened in both of those situations? They're eliminations. I lost a leaving group, bromine. I also got rid of a hydrogen, and in place of that, I got a pi bond. But I did it again. Right? So it's just two back-to-back eliminations. Those two back-to-back eliminations happened in such a way where I formed a triple bond. Is that triple bond any different than really an alkene? No, it's just the formation of a pi bond. So when we think eliminations, we tend to think again in the narrow concept of we make alkenes. No, we make pi bonds. A pi bond can be between most any two atoms. Right? And we can have more than one pi bond. So triple bonds are just as likely to form from elimination reactions as are double bonds. But to do the triple bond, I have to do two eliminations, which means two hydrogens must be removed and two leaving groups. If I only have one leaving group, I can't make a triple bond. Most of the systems that we've looked at have only had one leaving group. That's why we ended at the alkene. Kind of make sense? Okay. The two starting materials. Oh, I probably shouldn't even be saying this because I always get it wrong. Yeah. Let's see. Crap. I don't remember. You may hear reference to geminal, and I think that's spelled right, vicinal. Okay. What those are referencing is the location of those two leaving groups. If the leaving groups are on different carbons or proximal carbons, that would get called vicinal. Yeah? Oh, cool. If they're on the same carbon, they get called geminal. Okay, so you may hear reference to those words, and maybe there's a YL there, I'm not positive. Okay. I don't expect you to know that. I just expect you to be aware of that terminology. When it comes to kind of special terms like that, as you've seen potentially in lab, I will include the term and a representative structure. Right? Because I do expect you to be able to interpret structures. Okay? So those are eliminations. Well, what about substitution? Okay, it turns out these can also be super useful in substitution reactions. And that one gets a bit odd. Okay? Why does it get odd? Well, are alkenes acidic? What is their pKa? Like, you didn't tell me to memorize that. I kind of actually suggested that you should memorize it, and you interpreted that to be you didn't need to memorize that. Which is admittedly a fair interpretation. Okay? It's about 40. The pKa of an alkane is 50. For an alkene, 40-ish. Okay? Those pKa's are so high as to be completely non-acidic, and we don't even consider them as acidic. Okay? The alkyne dramatically drops in acidity. It drops to allegedly in the 25 range, and I'm not sure I've got that number right, but I think that's what I put in the slides. Okay? Hopefully I looked that up. Okay? What does that mean for its acidity? It's more acidic than an alkene. Okay, fair enough. Okay? It potentially makes it reactive. These are alkynes in the presence of sodium amide, okay? An incredibly strong base. Okay? So let's go through and see what happens if I had sodium amide floating around. Okay, well, if that's a strong base, it could potentially remove a hydrogen. The acidic hydrogen would actually be located where? At the extreme end of the alkyne. The result being a negatively charged carbon. Do we like negatively charged carbons? Why do you think negatively charged carbons are a bad idea? They're unstable. Good start. Add to it. Why are they unstable? Because they're higher in energy. Don't answer that. Size and electronegativity. Carbon's relatively low on the electronegativity scale, which means it doesn't want to steal electrons from other atoms. Okay? Its size, it's relatively tiny as far as size goes, so it shouldn't be able to stabilize that negative charge, which would suggest that the reaction I have shown here completely nonsensical and doesn't work. Okay? Yet, of course, there's a reason I'm talking about it. That reason is that it does work. How would I know it does work? We could try and make the argument between the negatives and go through our rules. Charge, stability, size, all those fun things. Stability, charge, size, electronegativity, and compare the nitrogen to the carbon. Okay? And we would go through, and every time we'd say the nitrogen is more stable, which would suggest what happens with our reaction. Whoa, that was supposed to be an eraser. It heavily favors the reactants. Okay? That would be our interpretation. Okay? Well, one of the things that we aren't taking into consideration, and this is where we run into memorization, okay, is the hybridization effect. Does hybridization affect your electronegativity?
Yes.
Yes. How much does it affect it? Well, about half. The numbers aren't going to be useful if we just say how much it affects it. Okay, so really what we would need to do is get into a quantification of it. A quantification that we would find in, say, pKa's. The pKa for our alkyne, we already listed, was what? 25. And because, again, we memorized the pKa for our amine, it's 36. What does that mean for our reaction? It heavily favors the products. Okay? By roughly, what is that, 1,000 times, because we're on a log scale. Okay? Why is that now useful for us? Well, what have I generated? A negative carbon. What kind of species are negative? Nucleophiles. What could I use a nucleophile in? A substitution reaction. And with this negatively charged carbon, I can now take a standard carbon structure where I could only add heteroatoms, halogens, or nitrogen, or oxygen. Now I can add carbon structures to it. Okay? This is roughly the equivalent of being able to say I can take an I-beam and attach it to another I-beam. Okay? I can now make things larger. I can make, what are those tall things? Skyscrapers. Okay. This is pretty important. Carbon nucleophiles make larger carbon structures. And if you go through and look at virtually every organic molecule out there, there's lots of carbons in them. Okay. How do we get those larger carbon structures? You have to have negative carbons. Okay. So the negative carbon here in the alkyne now becomes insanely useful synthetically, and it shows up in lots of cases. Okay. To give you an idea of the rarity of the negative carbon, it is so rare that there's less than, well, that's probably an overstatement, but probably less than 10 reactions that involve negative carbons, okay, in all reactions. Well, yeah, that's not that big a deal, 10 reactions. Roughly 9 of those are named after the person that discovered them. Okay? That's how rare they are. They're so important that we actually name the reaction after the person that discovered them because, like, you shouldn't be able to do that. Okay? So they're incredibly important reagents. You see them show up a lot, particularly in biochemistry, because of what has to happen in biology. You take CO2 and you turn it into sugar, like glucose, okay, which can then be an energy source for the rest of life. Okay? okay, which gets us our proteins, gets us our carbohydrates, gets us our DNA. All of that is ultimately originating from carbon dioxide, a single atom of carbon. So we have to be able to change the reactivity of our carbons to connect them out into larger structures. So negative carbons are super, super important. Okay? That also means they're pretty insanely reactive, so they're awesome for nucleophilic substitution reactions. Okay? Oh, look at that. Damn it. See, spelled right from the beginning. Okay? So our intermolecular versus our intramolecular, this is what I thought should have shown up a little bit earlier. This is a bunch of text the textbook put together. Ultimately what this says, intermolecular happen relatively quickly, or commonly. Intermolecular means multiple molecules. So if you're looking at a reaction, you should probably do multiple molecules. Intramolecular tends to not happen because that's within the molecule. Okay, those tend to be more difficult to make and break bonds solely within the molecule. Okay? Something has to polarize the structure to force it apart. So given an option, you probably want to have inter instead of intra. Okay? Again, there are exceptions. Those exceptions ultimately hinge on the stability of the potential products that would come out of it. Okay? So if we looked at an intermolecular reaction between this compound, or starting with a single compound here. Okay? As an intermolecular, what happens? Well, a second molecule of it comes in and reacts. Negative to positive, we kick it out. Notice we're running this as what type of mechanism? Why is this running as an SN2 and not an SN1? So one answer, it's one step, so that works. It's shown here as one step, so we're saying it's an SN2. Okay? No carbocation. I didn't show a carbocation, so it must be an SN2. Both of those answers relied on the fact that I showed you what happened. Okay. Now how do I know it's an SN2? And don't tell me because you only showed all the arrows there. The only information I have to work off of now is the substrate and the nucleophile. Okay? So when you're trying to look at a reaction and decide what mechanism to run, you need to be looking at the nucleophile, usually first, because the nucleophile is almost always charged. Okay? That charge is a big tip-off onto what mechanism you run, because if it is charged, what kind of mechanism should you expect? I don't quite accept SN2 yet. Actually I do, because I said nucleophile. If we have a negatively charged species, we should be expecting a bimolecular reaction. If I then specify that that is a nucleophile that is negatively charged, we now know SN2. Right? Why? Well, what do I need in an SN2 reaction? I don't accept strong nucleophile because that's ultimately the answer. Why do I need a strong nucleophile? SN2, there's a big word you should be remembering tied to it. Backside attack. Okay? The leaving group leaves as the nucleophile attacks, which means the leaving group is getting forced off by the nucleophile. Okay? When was the last time somebody weaker than you forced you to do anything? Not quite sure I want to. Yeah,
kids can help you do anything.
Maybe, yeah.
Not a great example, especially if someone has kids.
What are those kids doing, though? They aren't actually weaker than you in that case. What are they doing? They are stronger than you emotionally, so they are taking advantage of your emotional weakness. The kids are stronger than you. Your managers are at work are stronger than you because of your emotional weakness that you don't want to get fired from that job. Okay? The instant the powers flip, where you are now stronger than somebody else, you aren't going to do what they ask. Okay? So to do an SN2, you have to have a strong nucleophile, otherwise it doesn't happen. Right? I have a negatively charged structure here, which means strong. There we go. So based on looking at the nucleophile, quote-unquote base, we know we're doing an SN2. Well, what if we couldn't identify the nucleophile? Well, then we go through and look for substrate. What kind of substrate do I have here? So the substrate is now the partial positive. So we looked for our partial negative, which in this case was formally negative. We can then move to our partial positive, okay, being the carbon where the chlorine was attached. Okay. Classify that substrate. Right. This becomes a language barrier. We could go through and say alkyl halide, that's naming the functional group. I don't want the name of the functional group, I want you to classify that structure. Primary is the word we'd be fishing for there. Okay. So what we're looking for is primary, secondary, tertiary, because ultimately what those things are tied to is now a steric hindrance, or the electron bulk that would potentially block the backside attack. Here, since it's primary, what would we say about the backside?
Exposed.
It's exposed, which would then mean very little steric hindrance. That's awesome for a backside attack. So when we evaluate both the nucleophile and the substrate, both pieces of evidence tell us backside attack. That runs an SN2 mechanism. Okay? We could go through and look at the solvent, except in this case, there is no solvent specified. Okay? So that's why I go through and look for the nucleophile first, because it usually jumps out as the most reactive thing, because it's typically negatively charged, though it doesn't have to be. Okay? The substrate is almost always hidden with charge behind an electronegative element, so that's almost always more difficult to find. Okay? So I would start nucleophile, then substrate. Then if I have to, I'll move for the solvent. But I don't look to the solvent first because the solvent sometimes isn't given. So this isn't an order of priority. This is literally what do I find most useful to get to the answer. Right? When we think about stability, that was charge, size, electronegativity. The order is a critical importance there. That's not utility. Here it's a utility. Okay? So we want to run an SN2 mechanism. If we go through and look at the results of all of that, okay, we've produced a product. Okay? What do you guys think? Is that a reasonably stable product or not? Doesn't look that bad, right? It's just a bunch of squiggly lines. What are those squiggly lines? The lines are not carbons. They're sigma bonds. And what can sigma bonds do? Rotate. So what we're looking at here is not two nice normal lines lining up next to each other. We have two pieces of spaghetti being flung at each other, and they magically hit perfectly aligned. That's starting to sound a little bit less likely. Right? It could happen, but that's a little bit less likely. If I take those two pieces of spaghetti and throw them up in the air near each other, more than likely what would the spaghetti do? Fall back. Probably on itself, forming a ball. Turns out chemical molecules will do the exact same thing. Okay? This is an intramolecular reaction. We just said that doesn't happen. Why is this allowed to happen? Because Mike said so. Nah, well.
Greater stability?
What do you mean greater stability? The ones that we said weren't allowed to happen were 3-membered rings, which we showed an exception to. Okay? 4-membered rings. Why are 3- and 4-membered rings not likely to happen?
Because of bond angle?
The bond angle. There's a bond strain, an angle strain to force those to happen. Why is this one okay? It's not a 3- or 4-membered ring. In fact, it's a 6-membered ring. And what did we learn back in Unit 1 about 6-membered rings? They were the most stable. Okay? the product here generates a very stable cyclic structure. So when you generate stable cyclic products, they're allowed to happen. Some of that argument has to come from prior knowledge. You needed to know that a six-membered ring was more stable. Right? Did we talk about why six-membered rings were more stable? Yeah, that was our angle strain. Right? So to get to this point, ultimately what you needed to do was probably just memorize six-membered rings were lower in energy than their counterparts. Right? And you have the answer. Do you have the background knowledge to explain why that is an answer? Yes, but that requires a lot more work behind it. Okay? So you get lots of kind of layering of information in to ultimately get to that answer. Yes?
I have a question on the last line. If you could run the reaction again on the second structure, would that make more sense?
Could we run this reaction again, as in doing what?
As in the chlorine leaves and then the oxygen.
Could the oxygen then attack, making a really, really big ring, right? Right? Would that be more stable than this ring?
No, but it would be more stable than the other one, right?
So now let's add the next kind of layer on this. To get here, what did I have to do? Two pieces of floppy spaghetti formed a bond. Now those two pieces that they formed that we said wasn't a good thing to form have to now react again, where now the two ends that are now even further away from each other have to somehow fold back perfectly to each other. Right? Yes, it's possible, but you're now starting to move into the nuances of probabilities. Yeah, you're there. 0.5% of the time we do form that. Is that a useful product to be analyzing? More stability in the long strand, that is a harder question to answer. You've limited some of the rotation by doing so. It's not as stable as in this situation. Right? So, yeah, it could be more stable. The argument that we could run into there would be the same argument that we could get. Whoops, that's not what I wanted. This is what I wanted. Yep. What reaction did I run? How do you know this is an SN1? Doesn't an E1 have an intermediate? Rhymes with yes. Yes. Right. Then, did that just now sink in? Okay. How do I know this is not an E1, but it's an SN1? The product of an elimination reaction is a pi bond, and pi bonds are higher in energy than sigma bonds. The product here is lower in energy than my reactant. This has to be a substitution, not an elimination. Right? When we look at the SN1 mechanism, right, we're talking about the intermediate, right? Right, so let's kind of ignore for the moment the rest of this stuff. Well, that's apparently an off-white background. That would most likely happen with a tertiary. And we said it would not happen with a primary, right? Right? But doesn't the primary happen faster for that next step?
Yeah. But it takes so much energy to do that.
Is the first step allowed? No. Go away. How do I get my stuff back? Was the first step allowed?
Yeah.
Right? In this case, that step wasn't likely to happen. Sure, the next step may work, and it's going to be a more likely thing to happen, but I don't get there. So it's not relevant. Right? So focus more here. One thing you might be thinking of is this is now generating long chains of carbons. Have you seen long chains of carbons before? For those of you that have studied biology? Yeah, like lipids? Well, we just said we can't form long chains of carbons. What the hell? Why does biology get to do it?
Because they create double bonds.
Because of branching?
Because of enzymes. Because of millions of years of evolution, life has created specific molecules that are now designed to do stuff that shouldn't happen in the lab. Okay? This is why biology has a big upper hand over synthetic chemists. We don't have the control to say, well, I want this group to go to this side and only this side. Biology does. Okay? And ultimately, it's not biologists. It's chemists that study biology, that steal biologists' stuff. That's probably a better way to say it. So biologists have cooler tools, chemists have cooler knowledge. That's actually kind of cool. I like that. Okay? Kind of makes sense? It's an interesting question. So, at that point, yippee, we're officially done with all the content for the exam. Right? It is now all done. You have it all. Now it's a question of manipulating and using that content for the exam on Monday. Yay. Okay? So, the last sequence of slides is ultimately just a summary. Right? So what I've got, what I've gone through and done is provided a slide for a mechanism for an SN1. We've seen this slide already. This is the general mechanistic steps for an SN1. Okay? Notice the nucleophile, not strong. Okay? The substrate, unfortunately, it was a horrible choice because that's primary. That wouldn't generate a stable carbocation. So who's perfect? Right? So your nucleophile doesn't react first. The leaving group leaves. This makes the assumption that we have a stable leaving group. Okay? So anytime you run your substitution reactions, that's cool. You can have the leaving group leave, but at least pause for a second and be like, that's an okay leaving group. Okay? And as long as you say okay, then you can continue to move through. We have a carbocation. That step is the slow step. That's why we get the rate that we see. It's dependent solely on the concentration of the substrate. Our nucleophile can then come in and attack. Depending on the nucleophile, it may or may not have that hydrogen attached. If it does have the hydrogen attached, I have to get rid of it because the nucleophile would then be positive. So I'd have an extra step in the mechanism. That extra step is typically going to be an acid-base step. Okay?
So the nucleophile would be the slowest step?
I said the leaving group leaving is your slowest step, the very first step. Okay? We have to form the carbocation. So everything about this mechanism centers on the carbocation because that is our slowest step. So everything we do about looking at substrates, at nucleophiles, at solvents, is all about, does it affect the carbocation? If it does, that's an important thing to evaluate. If it doesn't, I ignore it. For instance, the nucleophile. Is it involved in the formation of the carbocation? No. Which means I don't care about the nucleophile. It's irrelevant to my argument. Okay? Having a more substituted carbocation, does that affect the carbocation? Yes. Is that going to be an important thing for me to evaluate? Incredibly. Okay? So when we go through and... Ooh, that happened not quite the way I thought it was going to. What we'd be doing is looking at all of the pieces that are tied to our substitution. We have a substrate, we have leaving group, we have nucleophile, we have solvent. What are the things that we want? So for a substrate, I want the most stable carbocation, okay? Which could mean tertiary. Notice I'm not saying tertiary here. Why? Resonance could also contribute. So tertiary with resonance is more stable than secondary with resonance, than primary with... And it's too many words. We already wrote it up. So all I got is stable carbocation. Leaving group, it needs to be there. So that's kind of a dumb thing to write, but hey, it's there. Nucleophile. Well, in the slowest part of my mechanism, I don't care about the nucleophile, so it is typically weak or irrelevant. The solvent, we have our 3 solvent classifications. The polar protic solvent generates the largest partial negative of all of them, which stabilizes the carbocation. Okay? What happens with the stereochemistry? Okay? Or potential complications. Well, the stereochemistry, we get a loss, in quotes, we get racemic products. What does it mean if we have racemic products? No optical activity. So we have to pull back from our knowledge in the previous sections to pull that forward. Right? Complications. Because we have carbocations, we have the possibility for rearrangements. This does not mean every time you do an SN1 reaction you should rearrange. It means they are possible. Right? If we move to the SN2, this one is what I was expecting the SN1 to look like. We've got our mechanism summary shown. Notice I'm showing a transition state. This is not a step. Okay, this is not 2 steps. This is showing what it looks like as it's happening. So it is a single step reaction. The key word there is backside attack, or words, because I guess that's 2. Okay. The nucleophile has to come in and attack from the backside. Okay. That helps you out when you get to stereochemistry. That also helps you out when you think about the benefits of this. That also helps you out when you look at the substrate and the nucleophile. Okay. So if you have those keywords there and understand their meaning behind them, you can use them. If you don't have that meaning, you can't use them. So substrate, smaller is better, right? Because it's attacking the backside. Right? The bigger the backside, the harder it is to gain access. Leaving group. Again, pretty dumb. It needs to leave. Okay? The nucleophile must be strong. What makes it strong? Charge. What charge? A negative charge. How do I know nucleophile needs to be negatively charged? Because that is the definition of a nucleophile. Knowing the word can help you come up with the meaning and what it needs to be. Will it always be shown as a negative? No. Is this a strong nucleophile? Yes. Why? It's negatively charged. Is this a strong nucleophile? Well, it's not negatively charged. Yeah, it is. It's an ionic bond. All the way back to Unit 1. You have to be able to acknowledge what kind of bond types there are so that you know what happens. If that's an ionic bond, that immediately dissociates into the ions, Br minus, Na plus. There's my negative charge. Okay? So you have to be thinking about all of those bond characteristics all the way up. Solvent. Okay? When we looked at the SN1, the solvent was protic because it stabilized a cation. Okay? The solvent choice for SN2 really comes back to the nucleophile strength. It has to be strong. Okay? If I use a protic solvent, it's not strong anymore because a protic solvent supplies H+. That kills the negative. Okay? If I use a nonpolar solvent, so it doesn't affect the negative, it now literally doesn't affect the negative, which means the negative never makes it into a situation where it can react. They have to be able to interact. That means nonpolar is bad, protic is bad. I only have one choice. Okay? It is the least worst decision, okay? Which is sometimes the best. It's usually the best, isn't it? The least worst? I think it has to be the best. Right? Yeah. Stereochemistry. Because it does backside attack, it inverts. Okay? When does it invert? It always inverts the structure. Okay? That does not mean necessarily the stereochemistry inverts. Because if there is no stereochemistry, you can't invert it. The structure still inverts. Okay? The benefit of an SN2, there are no rearrangements. Okay? So that can make life a little bit better. Okay? So we've looked at them independently. Now what happens when I'm trying to decide between them? Okay? So SN1 versus SN2. We now have all of them summarized out on what things we should be looking for. So where do you see differences between the SN1 and the SN2?
Substrate pattern.
Okay? We could look at our substrate patterns. Okay? The methyl reacts faster than the tertiary. Okay? For SN2. The tertiary reacts faster than the methyl for SN1. So if we can identify those key differences, that can help us get through our mechanisms or decide on what mechanism to run. Make sense? Where's another big difference? The nucleophile. Where's another big difference? The solvent. You mean the three things that I said that I would go through and look at to distinguish between them? Yes, exactly those three things. This is why I told you those. Right? It may not be in order here because this order was kind of arbitrary. That was kind of dumb. I should fix that. Right? Once you've identified the mechanism, then you have to be concerned about what that means as far as stereochemistry, maybe even rates, okay, complications. So you have to be concerned about those after the fact. Right? The E1 summary. Right? You guys get the idea on this? Should I actually be talking through these? Yeah? Okay. So in an E1, our substrate, again, it's the one type carbocation. Okay. Same thing as an SN1. So I have to form a stable carbocation. The leaving group, as usual, it should be good. Right? Now all of a sudden switch, I don't say nucleophile anymore. Why is it not a nucleophile? It's still negatively charged, potentially. It's reacting with a hydrogen. Nucleophiles are negatively charged, but they react with not hydrogen. Bases react exclusively with hydrogen. So we get a slight change in the wording. If you understand the definitions, it can help. Why do I not care about the base in this case? It's all about the stable carbocation, and the cation happens without a base. It's just the leaving group leaving. Okay. Solvent, typically polar protic. Okay. After experience with looking at these things more and more, I would be very leery about deciding on an elimination reaction based off of the solvent. Okay. The reason being will happen when we move into the E2. Okay. Theoretically, I didn't screw it up on the slides. Okay. What happens with the regiochemistry? We mainly get trans. Because we have a carbocation, the hydrogen that's removed can be removed from either the upside, forming a bond with the p orbital above, or we could do a sigma bond rotation and bring the hydrogen to the bottom side. The result is that both the cis and the trans are allowed. Okay. However, the cis is not favored because it's higher in energy than the trans. And when we're forming an alkene, we're forming something that is already higher in energy. Okay? If you have to go upstairs and you have your choice of going up 1 versus up 60, and you're not trying to work out, you'll probably pick 1. Okay? We want to go up the smallest amount possible. The other word that comes into this is Zaitsev's favored, okay, which is really just saying form the most stable double bond. Okay? Our elimination reactions are endothermic, form the lowest energy double bond possible. Okay? This says benefit. I would argue that that is horribly labeled, because would you consider a rearrangement a benefit?
No.
No, that's probably more along the line with a complication of this, but I'm trying to mimic patterns. We form a carbocation, you have to think about rearrangements. Sure. Yeah, we can use Zaitsev exactly with the slide here. So what is Zaitsev talking about? When we go through and look at this, we have a hydrogen that we can eliminate to make the double bond. That looks like it would produce this purple structure. Right? If I rotate the sigma bond first, so that the hydrogen is now aimed away, and then do, whoops, I wanted it this color, and then do the elimination, I would end up with the trans. So rotate, okay, then eliminate. That's kind of fun to say, because they rhyme. Okay? Both of those would work. Is there another hydrogen that I could remove? I could also eliminate that hydrogen, which would result in this structure. I could do all sorts of rotations about that. It's ultimately not going to change the double bond because that double bond, the orange one, does not show cis-trans isomerism. So it doesn't matter with a rotation. Okay, so there's three possible products that can come out of this. Okay. Zaitsev went through and said, well, the product, this, I just remembered it, the product that is formed is the product generated by removing hydrogen from the position that already had the fewest hydrogen. Okay. So look at our carbocation, look at the beta positions. The product that is formed is the product that is formed from the removal of a hydrogen that already had the fewest hydrogens. So the beta position up and to the left is 2 hydrogens. The beta position down has 3 hydrogens, which means the 2 is the favored product. Okay. Zaitsev rule technically then does not differentiate between the 2 top structures. Okay? Because it's really just talking about the placement of the hydrogens. Okay? The reason why it's kind of a silly thing to do, or reference that rule now, is that was discovered before we knew about electrons. And OChem is literally only about electrons. So we are naming this rule for a product formed based on somebody that didn't even know electrons existed. That's a little bit weird. Okay? So the argument that I've made in class is that you shouldn't memorize that at Zaitsev. You should remember, make the most stable double bond. Why is it the most stable? You've buried the electrons. You've made them most difficult to get access to. Okay? If we look at the orange one, those electrons are on the outside of the structure. Both of the black drawn ones, the electrons are on inside the structure. The electrons on the inside are harder to get access to. Those are more stable. Okay? Which is better, blue or purple? The blue one is better because of a symmetry argument, if you want to run it that way, where you've embedded those electrons in behind, and it becomes a little bit more difficult for the electrons to get access. Okay? So really all we're saying with Zaitsev is make the most stable double bond. Okay? The reasoning behind the double bond has to do with the number of substituents. Not primary, secondary, tertiary, the number of substituents. The orange one has how many non-hydrogen substituents on the double bond? 1. The blue box has how many non-hydrogen substituents? 2. The purple arrow product that's black has 2. So the orange one makes no sense because the other two have 2 substituents between the purple and the blue. Blue is more stable than purple. There's the argumentation. Make sense? Right. But how you will almost always see this referenced, say on Chegg or online, would be Zaitsev. Okay? If we moved into kind of the next part, rearrangements are possible because you form the carbocation. Okay? The other big, massive issue with E1 is it directly competes with SN1. They are both doing identical processes. The only thing that differentiates them is the second step. The second step that literally is irrelevant to both of their mechanisms. Okay? So it becomes very difficult. If I'm going to run an SN1, almost always I'm getting an E1 product also. Okay? So it's a horrible reaction to run because we get multiple products in the SN and in the E. Right? But then I also get both E and S. Okay, so theoretically, I could run a reaction and get 4 products out of it, only one of them being the one I want. Okay? The E2 summary, because it all happens at the same time. I guess I didn't add curved arrows. Let's add curved arrows real quickly to the last one. Sorry. Leaving group leaves. We've got our carbocation. We remove the hydrogen. Notice I'm not showing a base pick up the hydrogen. That comes to my personal preference. The textbook and the internet may have something different to say about that. Right? They always do. Nobody likes me anyway, so that's why. We could show a base. It's typically going to be your solvent. Okay? So it'll probably be a protic solvent. You'll have the oxygen in there. So ethanol is a good solvent. You might see water, but probably not. You're probably seeing something like an alcohol. Right? That step isn't important to me to show because it's not relevant to the mechanism. Right? The part that becomes important when we move to the E2 is that I have to remove that hydrogen at the exact same instant that the leaving group leaves. Right? The problem with that is that a carbon-hydrogen bond is not polar. That's not an easy bond to break. Right? So what could I supply? Heat could help weaken that bond, which works great for the elimination, the E1, and it can help for the E2, but we typically want something else to really rip that hydrogen off. Nothing to do with the solvent. Could be one of our categories.
Strong base.
We want a base, okay? And typically we want a strong base, so it needs to be negatively charged to remove that hydrogen. For the E2, I would show that base being involved because the base is the most reactive thing there because it's charged. Right? So the base comes in, rips the hydrogen off, and we can kick the leaving group off at the same time we make our pi bond. We get the option for two products. Okay? This is where the mechanism and unfortunately stereochemistry comes into play, so we'll wait for that in a second when we get down into the regiochemistry answer. The substrate, because we're trying to make a stable pi bond, our substrate changes a little bit. Okay? It's a two-type mechanism. So for SN2, we wanted sterically unhindered backside. But here, it's not necessarily, yes, it is a backside attack, but I'm concerned about making a stable pi bond. If I remove the hydrogen, because we had it orange before, out here, does that make a stable pi bond? No. So what happens? The activation barrier for that acid-base step is now higher than for the other one, and we end up not seeing that product. This means when we think about the substrate, tertiary leaving groups are actually better for E2 mechanisms than primary. So it conflicts with the SN2, which is pretty awesome because if it didn't conflict, we'd run into the same issue that we had with the SN1 and the E1. They'd always run simultaneously. But now, because there's a conflict here, what happens? The E2 does not compete with the SN2. Okay? There's a difference in their substrate requirements. Okay? Leaving group, it's got to be good. The base, it needs to be strong because, again, we're forcing the hydrogen off. Solvent, this is, thankfully I put it in here nicely. Okay? It's misleading because it's a two-type mechanism. We would almost always expect a polar A product, and yet normally always we get a protic solvent. And we get a protic solvent always because of the base. Right? And it's because of the identity of the base. The base is almost always like an ethoxide. Well, why would that be a problem? Where did I get the ethoxide from? That came from reacting ethanol, a protic solvent, with something like potassium metal. It does an acid-base reaction and removes the hydrogen from some of the solvent, but not all. Meaning there is almost always some of the alcohol remaining. Meaning, don't base your mechanism decision for an E2 on the solvent, okay? Because it will mislead you. Sometimes you'll see it as aprotic, Sometimes you'll see it as product. In fact, typically it's written as product. Okay? So don't evaluate using solvents to decide your elimination reactions. It's a bad idea. Regiochemistry, okay, it's dictated by the alignment of the leaving group and the hydrogen. Okay? We have to have that anti-periplanar alignment. So we can get trans, we can get cis. It all depends on the alignment of your hydrogen and your leaving group. They must be anti to each other. If they're not, we don't get the elimination. Okay? We will still typically favor the Zaitsev product, okay, the more substituted product. Okay? But between cis and trans, it's dictated by the alignment of your leaving group and hydrogen, okay, which can be tricky to see. The complication, you can see a Hoffman elimination. I'm going to just completely ignore that for this test, so don't stress about the Hoffman elimination. Maybe we'll talk about it after the exam. When we're trying to decide between the two mechanisms, we've got them listed out here. Okay. The big difference on this thing is that in the substrate pattern, I've given the example there for the E2. Okay. I don't know why the zero area is on there. You can't eliminate that one. That makes no sense. Okay. You get the same substitution pattern for E1 and E2. So you can't use the substrate to distinguish between those two mechanisms. What would you use to distinguish them? The base. Interestingly enough, when we talked about this, I said when we try and evaluate which mechanism we decide on, what did I say you should look at first? The nucleophile, which is equivalent to our base. Why?
They're opposite.
It really allows us to distinguish the mechanisms pretty cleanly. Okay? The solvent becomes much less important for the E1, E2 mechanisms. Okay? So I would pretty much just ignore it. The polar product, I think, is also kind of misleading there. Your stereochemistry is on there. You got your Zaitsev products on there. Okay? Okay. This gets us again to that table that the textbook presented, okay, that I went through and said is nice to have, okay, but I don't like the things in it. What I went through and did was something more along these lines. Starting with nucleophile or base, ultimately the same thing. That was the first thing I said you should look at. The next thing you should look at would be the substrate. Notice the leaving group is in tiny, tiny font because it's always going to be, it always needs to be good. So that's like a, before you even start the reaction, make sure it's good. Okay? Then we'd look at our substrate, then we'd have our solvent. Heat, when do we typically need heat? For our elimination reactions. E1 is the most common place for our heat, but any elimination typically wants heat because you're breaking a difficult bond. E2, it's less important because the base is what's breaking that hydrogen off. Okay? But the heat can help. What you would then go through and do is total to say which of those came out. Okay, so the argument that I would make is you should go back with those previous slides and say, okay, where are things important? So for the SN1 nucleophile, it should be weak. For the SN2, it should be strong. Why is it not important to evaluate the nucleophile strength for E1 and E2? Because it doesn't say EN1, it says E1. The end was for nucleophile. That's why it's important for the substitution, because it's SN. I don't want a nucleophile in the elimination. Okay? I don't want a base in the substitution. Okay? What I want is a nucleophile. It needs something to attack it. So Na is there. We're looking at 1 and 2 again, so weak and strong. The leaving group should just be, here, no, I got it. G-O-O-D. It works. Substrate for the SN1. What kind of substrate do I want? Tertiary is better than secondary. Arguably, we should say cation. While the tertiary being better than secondary is true, that doesn't take into consideration all the resonance effects. So if you include the idea of cation in that, that can help you. What do you want for the SN2? Less steric hindrance, so that's where we go 0, 1, 2. Notice the 3 isn't on the list for SN2, and the 1 isn't on the list for the SN1. It's because they don't happen in those cases. Right? E1. It's a stable carbocation. You mean the same thing as the SN1? Yep. For the E2, tertiary is more stable because I'm looking at forming the most stable product, the alkene. So tertiary is faster than secondary, faster than primary. Right? Solvent for the SN1. I'm going to pretend I heard that. Pretty sure I did. For the SN2, polar aprotic. And for the eliminations, say misleading. I think I heard a boo. Okay. So I would be careful evaluating the solvent if I thought an elimination reaction was going on. Okay. Heat. Where is heat important? Heat's really relevant for the last two. And here I can do this a little bit better. Right? Because it's really important for the E1. It's a little bit less important for the E2. Spelled, yeah. SN1 and SN2, not as important. It can show up, okay, but not as important. I don't feel like writing important all the way out. So every time you look at a reaction where you aren't told it's SN1, SN2, E1, or E2, you should be pulling up this kind of chart and using this to determine which mechanism you think it's going to run. Really, it's going to boil down to those three questions. Nucleophile, substrate, solvent. Okay. Sometimes you'll get into the nuance of having to deal with heat. Sometimes you might have to evaluate the leaving group, but that's not going to dictate the mechanism. Okay. That'll just dictate that your reaction was actually allowed to run. Okay? Kind of makes sense? Okay. So when we move into that next slide, this is now just breaking them out. The strength of your nucleophile or base helps you decide the order of the reaction. Okay? It's going to be bimolecular if it's strong. If it's a nucleophile, well, then you do substitution. If it's a base, you do elimination. How do you decide between nucleophile and base? It's not charge because they're both negatively charged. It's size. It's what they're reacting with. Nucleophiles react with things on the inside of the structure. Bases react with things on the outside of the structure. That means nucleophiles need to be small to make it to the inside. Bases really don't care. Okay? But if I want it to only act as a base, I can make it big. Okay? So that can help me limit. If I only want a nucleophile, the good examples are iodide, chloride, and the BR one, bromide. Okay? If I only want bases, that's where it should be big and bulky. That's where we get the T-butoxide. The DBN and DBU don't stress about, but those are other names that you could potentially theoretically see that I would give you a structure for and tell you the name. Okay? After that, look at your substrate, okay, because that helps you differentiate. Your primary halide almost exclusively is SN2. Secondary halide, stop trying to compare because every single one of the mechanisms does a secondary halide. Move to the first rule. Okay? Tertiary halide is now a giant mix. Really all the tertiary halide does is it ignores SN2. Okay? So it helps, but it's not a big delineator. Solvents, we've got some differentiation there with our substitutions, but it doesn't really help with the eliminations. High temperatures tend to favor eliminations. Make sense? Okay. And then, as all things, we end in blackness. That is kind of depressing, huh? Okay. We still have a little bit of time. This is why I did pull up on my computer the practice exam. To get an idea, let's see if we can find one that covers those last remaining steps. Let's do it so we don't make people seasick and they're on the same slide, so it works out nicely. 12. Okay. If we take a look at 12, provide the reagent to complete the following transformation. Pieces of information you should be nailing down and writing down. What do you see? Pi bond, I'll accept that. What does the pi bond mean? Okay. Elimination, which would mean E1 or E2. Okay. If it was E2, we'd be looking for a base. So we could look to our answers and be like, booyah, that's a base. That's a base. What's the difference between those two? Right. This is that super frustrating thing where they wrote it as a formula, a structural formula as opposed to the structure. You have to be able to interpret these. The top one is a straight line, the bottom one fans out, which means the bottom one is ultimately the word that we've used on the slides is bulky. Okay. So the bottom one is large, the top one is small. What does that mean? D is, I don't accept better yet.
Always a base.
D is a base. A, on the other hand, could be a base, but it could also be a nucleophile. Okay? So A could be a dodgy answer because A could potentially do a substitution, and I only want elimination. Okay? So far, so good? What were the other two answers? Acids. So the complete polar opposite, so I must be right. Okay. What do bases react with? Acids. What kind of acids do they react with? The strongest acid. Where's the most acidic hydrogen in that starting material? The hydrogen off the oxygen is the most acidic hydrogen there. Yes, I may want to do the elimination. I may want to remove the hydrogen out here and that leaving group to form the pi bond. That doesn't mean I can. Okay? The most acidic hydrogen is the hydrogen on the OH, which means what happens? The base comes in, removes that hydrogen, and we get a negative charge. What does that then mean? That is a shite leaving group. Right? It wasn't good to begin with, and it now just became horrendous. Because if I then go through and try and remove the electrons, I have to kick those electrons onto the oxygen, meaning my leaving group is O minus 2. Minus 2. Okay? We can't count that high. If it's greater or less than the ones, negative or positive, however you want to look at it, if it's not 1 or 0, it's bad. Don't do it. Okay? So yes, it was good to roll all this information out, and that was helpful, but we also always have to keep in mind, you need to have a good leaving group. Is OH minus a good leaving group? No. O minus is even worse. So what does that mean the answer for A and D are? Those are actually wrong. What this really tests on, and this is why this question gets asked, is did you memorize, well, eliminations need base, there's my answer, done, move on. Don't memorize. Run the reaction that is there. If I have a negatively charged species, I need to neutralize that negative charge. Not with what I want it to react with, but what is most reactive. The most reactive is that hydrogen. Okay? So those are not your answers, which then means it has to be the acid. But I wanted a base for an elimination. What would the acid do? It would dissociate to give me H+. What do I have to neutralize H+? Lone pair electrons on the oxygen. making instead of OH. Is H2O a good leaving group? Yep. Now I can do the elimination. So now the question becomes, which acid? The answer is B, not C, because bromide is a nucleophile. If I did HBr, I wouldn't get the elimination, I'd get the substitution. Right? Jiminy Christmas. Right? Lots of different pieces that you have to scaffold through. Right? So you do need to take your time, write that information down. It is very easy to lose sight of where you're trying to go as you move through. Okay? So get the information written down, do the best that you can with it. Practice will help you get this nailed down. Okay? And sorry I took way too long to solve that, so I can't do 10.